Okay, dear students, welcome to the video here. And in this video, I am going to talk about the Kirchoff's law. So let us see what is this Kirchoff's law. You call it Kirchoff's law or you call it Kirchhoff's law. Okay, apple, apple. Okay, fine. So first of all, this Kirchoff's law, it actually consists of two basic laws. So the first law is junction law. The first law is junction law. Now, what is this junction law? This is a very simple law. Let us say there are like these three wires, they are connected here. So this point is known as junction. Okay. And because we had already studied this thing in electrostatics, that charge cannot be created nor destroyed. So the charge flowing through this wire and flowing through this wire should be equal to the charge that is leaving the junction. So junction law can be very easily defined that the charge coming towards the junction is always equal to the charge going away from the junction. So overall, it can be taken as that if I1 is the current coming from the upper side, I2 is the current coming from downside, so I can always say that I3 is equal to I1 plus I2. So this is a fairly simple law because current is actually a scalar quantity. So that is why it will be added in a simple algebraic method. So there is nothing to be thinking of here. So there is one very simple example that I can give you. Let us say we have this arrangement of the wire and the current here and here. This is 2 ampere, this is 3 ampere, and let us say the current moving from this wire is 1 ampere. And can you tell me what will be the current in this wire? You can pause the video and do it, but I am now going to explain you what is happening. See, 2 is here, 3 is here, so the total current in this wire will come out to be equal to 5 ampere. Okay, because current cannot be created nor destroyed. So this 5 ampere was going like this, and at the second junction 1 ampere goes to the upper side. So what is the left current? That goes to the goes to the other side. So this will come out to be equal to 5 minus 1, and that is 4 ampere. So this is as simple as it is. No, this is the junction law. So now we are moving to the second law, that is loop law. Okay, so this loop law is little different and I would say a little difficult. So let us clear the screen now first of all, and now I am going to write it here, loop law. So what is the definition? First of all, how we can define it? We can define this loop law is as the sum of all the potential differences across all the elements in a circuit or in a loop in a circuit is always equal to 0, is always equal to 0. So what do I intend to mean here is, let us say there are this is the circuit here. I'm going to take the example of a very peculiar circuit, and we're going to apply our Kirchhoff's law on this, and we are going to solve this question also. Do not worry. Let us say this is the circuit, and this is given as E1 R1, this is E2 R2. These are the internal resistances. This is the external resistance, capital R. Now we want to apply the Kirchhoff's law on this. So what does actually this definition means? This definition means that if you consider one loop here, so how to consider a loop here? First of all, just a moment please. Okay, so we were considering the loop law. Now how to consider a loop? So we have to first name it. So let us say this is A, B, C, D, E, and F. Now we are going to choose one loop first of all. So what is a loop? Loop is a complete 360-degree circuit. That's it. So how many loops are there first of all? So number of loops. Let us see how many rectangles are we able to see here in this diagram. So first of all, it will be A, B, E and F. Another can be A, B, not B. Another can be A, C, D, F. And the third one will be B, C, D, E. Now, these are three different rectangles or three different completely connecting loops in which the current is flowing. So these three are the loops that we are actually concerned with. But the order also matters here. So we have to take either this, and we must finalize one order. Are you taking it clockwise or are you going for the anti-clockwise thing? For example, this ABEF, if I'm concerned with this ABEF, so it will be ABEF. So loop is moving like this. So I can say that the loop is moving like this, isn't it? So the loop is going like this. I will name this loop as loop number 1. So this is the loop, and I have even given the sense to it, whether it is clockwise or anti-clockwise. Similarly, if I talk about this BCDE, so I think that we should not be violating a battery, but we can do that also. But instead of this, we should go for CB ED. We can go for this loop also. So you can run the loop in either of the directions. So let us go with BCDE only. Don't worry. Don't get confused. Okay. Now what is happening to BCDE? So we are moving like this and we are coming back here. So I am going to name this loop as 2. See, the sense of the loop actually doesn't matter much. Like you can take it clockwise or you can take it anti-clockwise, but it is always beneficial if you choose the direction of the loop as same as the direction of the current. So as much as possible, try to choose the direction of the loop which is same as that of current. But in this particular case, I have chosen it to be in the opposite sense, just to show you how we would be doing if it ever goes opposite. Okay. So now let us see. Once we have done this thing, now we are moving to the next thing now the next thing is there are some couple of steps that we are now going to follow. Please be very particular about these things. I know these things are not explained in any of the books properly, so please be very careful. Do all the questions step by step, and I assure you that you would be able to solve each and every question from Kirchoff's law. Now you see, the first step is to to identify the loops, and that we have done. Okay, this was actually the step number 1. So now we are going to step number 2. So step number 2 is to distribute the currents in all the circuit. Okay, in the complete circuit you need to distribute the current. Now how are we distributing the current? Let us say the current moving here is now taken as in this direction. So I have chosen it to be I1, and from this battery I will choose it to be I2, and this I1 and I2, it goes like this. And obviously at this junction what is happening? Both of the currents are connecting with each other, so they enter into this resistance and the current becomes I1 plus I2. I1 plus I2 from the capital R, and then it moves like this, and at this junction, junction number 2, that is E, the current divides itself into 2 parts, and obviously the even battery is giving out I1 current, so it has to gain I1 current. So I1 current will move up and I2 current is now going downwards. So I can say that all of the branches are now having the current that is distributed throughout them. So this is the step number 2 that we have completed. Now let us move to step number 3. Okay, now so distribute the current, and we have now distributed currents I1 and I2 and each and everything. So now we move to our step number 3, that is the major important step, writing the equations. Now for these equations we need to find the sign conventions first of all. So you can write A and we can write here resistances. So what we do in the case of resistances, like these are the resistance, this is the resistance R, and let us say the current is, the direction of the current is shown and the magnitude of the current is I. So we have to now concentrate on the direction of the loop. So how the loop is moving? Let us say the loop is moving in the same direction as that of the current. If our loop is moving in the same direction as that of the current, the potential difference will be subtracted, minus R. It will be subtracted. So this term, that is minus IR, will be added into our equation. Okay, I would be telling you why. I will tell you that also. Now you see, on contrary, if the other thing is happening like that, the resistance is R and the current is in the opposite direction. Now let us say the current is moving like this and the loop is moving just like the earlier one. The loop has not changed the direction, but the current has changed the direction. Now current and the loop are in the opposite direction. So what are we going to do now? We are going to add this term, that is plus IR, in our equation. Okay, so this will be the equation that we are going to add. Now why are we doing this thing? You see, let us say you are on a hill and a river is flowing there and you don't know anything about the height at which you are, like the sea level, height from the sea level. You don't have any idea about it, no? But there is a river flowing besides you. Now what is happening is you start moving along the river. Now river is flowing that side and you are moving along the river towards that side. Okay, so you are moving along the river. So what is happening? Obviously I can say that because the water is flowing in that direction and I am moving along with the water, it means my height is reducing with respect to sea level, isn't it? So if I am moving in the way the current is moving, I am definitely reducing my potential energy. I am reducing my potential, and that is why it will be subtracted. This thing will be subtracted. And if I talk about this thing, like when the river is now flowing downside, let us say river is flowing downside from the upside to me, and I am trying to move upside against the flow of the river, definitely I am increasing my height, so I am increasing my potential energy. That is why plus IR, the IR will be now added into the equation. So this is the reason why we subtract or why we add. But now the other element is battery. So what are we going to do with the help for the cell? So let us clear some space here now. And now we talk in the terms of battery. So B, battery. So what is happening now? Let us say this is the battery. Now in this case, we do not concern ourselves with the direction of the current, whether the current is in the right direction or left direction. It could be anything. We are least concerned about the current. But loop direction is very important. So let us say the loop is moving like this. So if the loop is moving like the way I have shown, first of all, it is going to encounter the negative side of the battery. So whenever it is encountering the negative side of the battery, we add the EMF into our equation. I repeat, when the loop is going to encounter the negative side of the battery first, we add the EMF into our equation. And what happens if it is in the opposite direction? Like let us say this is the battery and now the loop is moving in the opposite manner like this. So now it is encountering the positive terminal first. So that is why we are now going to subtract E in our arithmetic equation for the potentials that we are going to make. Why? Because if there is a loop and we encounter the negative terminal of the battery, this battery is now going to assist the current to keep on moving in the same direction. That is why this is going to increase the potential. But this battery, on contrary, is trying to stop the current. It is trying to make the current move in the opposite direction. That is why this will be subtracted. Okay. So this is how we do it. These are the simple principles that we must follow while we are writing the equation. So now what is left? We are now going to write the equations and we will see how we do that. This is the most important part that we are now going to start. Please be careful now. First of all, we have to write the name of the loop that we are concerned with. So let us say I am now choosing the loop ABEF. So I have named it here. In the loop, I can start from any of the point A, B, C, D, or whatever it is. But let us start from this point, and I am naming it like point number P. So I'm starting from point P. So first of all, we are going to encounter the negative terminal of the battery. That is why I have just taken across the battery itself, but you can choose any point. So if we are moving from P and we are taking this direction, that is the anti-clockwise direction for our loop. Now, what is happening? I will write it as 1, and this is now going to encounter the negative terminal of the battery first. So I am going to add this. So it will be plus E1 because the negative terminal of the battery comes first. And now I move along with the loop and I have reached the resistance R, and the current in that resistance R is I1 plus I2. So now the direction of the loop and the direction of the current is the same. So what is going to happen? I am going to subtract this thing. So the total current is I1 plus I2 into R. So I am going to subtract this thing because the directions are same. Now I move further according to the loop and there is no element till I reach R1. And in R1 I see that the current is I1 and the resistance is small r1, and the direction of the loop and the current is again the same. So I would be subtracting this thing I1 R1, and then I reach the same point, that is point number P. So I am now going to equate it to equal to 0. This is how I write the equation number 1. And let us now go to equation number 2. So equation number 2 is here, and now I am not going to change the direction of the loop. I will take the same direction as shown in the diagram now. I can start from any point. Let us start from the battery itself. So I go like this and this. So here I am going to name this point as, let us say, Q. So I am now going to start my journey from the point Q. So first of all, I am going to encounter the positive terminal of the battery, negative. So it will be negative E2 because I am encountering the positive terminal of the battery first. So now it moves and we come across the resistance R2. But here again, the loop is moving towards right and the current is moving towards left. So we have to add this also. Now we are going to add this and it will become I2R2. Isn't it? So now we move along with the loop and we reach this capital R, and we can see still the current is in the opposite direction with respect to the resistance R. So we are again going to add another term here. That will be this. And then I am going to reach the same point Q. So this will be equal to 0. So this is how I write the second equation. And now in this video I will tell you how to write this third equation also, and then we will take some examples in the next videos, you see. So here this is ABEF. Okay, I was supposed to write the names of the loop. So this is ABEF, and this loop is BC, BCDE, and I am maintaining the direction, the sense of the loop. And now I am going for ACDF. So I start from the point A, and first of all I am going to encounter the positive terminal of the battery E2. So it is minus E2, or let us say, to make it even more clear, let us start from the point P only. So first of all we will encounter the battery E1, the negative terminal. So it will become plus E1, and then the negative terminal of the battery, that is minus E2, and then the negative terminal, and then the resistance. But the current and the loop become, they are moving in the opposite direction. So I am going to add I2R2, and then this loop goes here, and now the direction is the same, I1R1 equal to 0. So this is how we write the third equation, and the loop is ACDF. Okay, dear students. So let us now see some of the examples how to apply these principles. Okay, dear students. So now let us take one example here, which I have taken from a very popular book for the IB. So let us see how are we able to apply our principle of Kirchoff's law here. So first of all, we are now going to follow the step number 1, and the step number 1 is distribute the current. So let us say that the current that is coming out of this battery of 9 volt is 1 ampere, is I1. So I1 moves like this and it goes like this. And in this battery, let us say this battery is making the current I2 to move like this. So I2 has to move like this. So what will be the remaining current here? So it will be I1 minus I2, because out of I1, I2 has moved into the other branch. So this branch is left with I1 minus I2. So this is how we have now distributed the current. And we can say these two resistances are in series. So we can treat them as 5 ohm together, that is 3 plus 2, instead of taking them as separate, because it will create a very big equation for us later. That is why we can just use 5 ohm instead of it. So the current here will be I1 minus I2, and it is now added with I2, so the current in this circuit will become I1, and I1 current is now returned to the battery from where it first started. So this is how we have distributed the current throughout our circuit. So step number 1 is complete now. Now what is step number 2? Step number 2 is to identify the loop and write the equation. That is step number 3. So let us identify the loop first of all, and let us show the direction. So the direction will be somewhere like this, that this thing, it will move like this, like this. Okay, so this is how the direction is moving. And so our equation for the first equation will be, we are now encountering the negative terminal of the battery first, so it will be plus 9. Now here you can see that the direction of the loop and the direction of the current is the same, so that is why we would be subtracting this thing. It will become 4I1, and as we move along with the loop, we are now encountering again the negative terminal of the second battery, so we need to add this also plus 3, and then there is no other element in the loop, so it will be equated with 0. So this is a very simple linear equation in one variable. We can just solve it. So it will be 9 plus 3 is equal to 12 minus 4I1. So this means 4I1 is equal to 12. So it will come out to be equal to 3 ampere. So simply we have found that this current is coming out to be equal to 3 ampere. Now we want to find the current I2. So for that we are going to have another loop, and we are now going to mention it. So this loop can be taken as moving like this, like this, like this. So how to write this equation? So first of all, this loop is now encountering the positive terminal of the battery. So we would be first taking the negative value of the EMF, that is minus 3. So minus 3, and now the loop moves up to this resistance. So both of these resistors are in series, so we can treat it as a 5 ohm. And so the current is this, the direction of the loop and the current is the same. So I1 minus I2 into 5, and then the loop reaches the same point and we can equate it to 0. From this equation we will find the value of I2. Minus 5, and I1 is taken to be 3 minus I2. It will be minus 3 minus 15 plus 5I2. It will become 5I2 is equal to 18, and from here I can say that I2 is 18 divided by 5, and which will become 3.6 ampere. Yes, so these are the currents in our circuit. So I1 is equal to 3 ampere and I2 is coming out to be equal to 3.6. So this is how we do it. So I have now tried to explain you the complete principle of Kirchoff's law, and also I have given one example to explain you the application of the Kirchoff's law. Now you go and try all the questions that were troubling you earlier, okay? And do let me know in the comment section if you are able to do them or not. So this is Professor Varun. Please subscribe to the YouTube channel. All the best.